Policy and infrastructure go together, and so do compute and competitiveness, which is exactly where we are going next. Our next speaker argues that access to advanced computing is the new sovereignty, the resource that decides who builds the future and who ends up buying it from someone else. Please welcome Roland Flan Vliet, co-founder and CPO of Near Field Instruments.
Thank you. Thank you, and great to be back. I just realized that it has been 30 years, almost to the day, that I moved to Berlin for half a year to do some research work at university. It's really good to be back. And also thanks to Minister Wildberger, because he made it so easy for me. Because at the last sentence he said that the end of the equation is power. And that's exactly what I want to discuss you about, because indeed AI is the perfect storm. Not just to use AI in all types of querying applications, but also for the European industry and also the hardware industry. And that's what I want to tell you a little bit about for Near Field Instruments. By the way, if there are any questions, please just interrupt and ask me. So, going to AI, more compute, more memory. We just learned it. More transistors, and a very important thing there is the exploding energy need. It's not just about making sure we have more compute. It should also be about a more efficient compute. But let's first look at how to get to these more transistors, how it is done. And I took an example of Apple. It's already a little bit older processor. What you want is more transistors. You want to measure more. You want to calculate more, so you need more transistors. So how do we do that? We just double the real estate. You see it here behind me. The difference between a standard processor and the Ultra, it's more transistors. But not because we make the transistor smaller, we just put more transistors on a larger real estate. And there's a limit to this. This cannot end. Because if you go to these larger dies, and you make them on a wafer, you can only fit a few of them on there. Now, if you have some contamination there, what happens? You immediately kill 1/10 or 1/20 of your production, instead of compared to these very small dies. It sounds a bit counterintuitive. We want to have more transistors, we make it on larger dies, and in the end you run down with your yield, your good die production. Now also, and this is what was mentioned in by the previous speaker as well, there's an energy problem as well. If you go to these hyperscaler AI setups, you see you go to 10,000, 100,000, a million, 10 million GPUs. In the end, you end up that you need a small nuclear plant to actually run such a AI factory. That is an undoable thing. Actually, I researched it. The total global demand of data centers today use already more energy than the whole of Germany uses, with its 80+ million people. It cannot continue like that. By just scaling down, we will cross at a certain point the amount of energy that the world can produce. Impossible. That means that we need to find any way to a different way to scale down, or actually scale up, not only by scaling down, I'll come to that later, but also make sure that what we produce in our transistors actually do not pose a bottleneck. And actually that is process control. So think that you want to fill a hyperscale facility with transistors. You take transistors, where we're talking about 3 transistors in the angstrom level, the 0.1 nanometer precision, times the number of dies, times the number of wafer that is produced in a wafer fab. In the end, it means that we have to produce 6 to the 10 to the 19th transistors well with angstrom precision. If not, we have a problem. And that's exactly what was mentioned by Minister Wildberg. It's not compute constraint anymore. We can have the compute. It's power constraint. we don't have the power, and especially if we have transistors that are not exactly according to spec. And I will tell you a little bit later. I won't go into the full detail of the calculation, but let's assume we have such a transistor, that one chip, and it's just off by 10 angstroms. And we're talking here about less than an atom size difference or failure in production. If you then calculate, in order to compensate for that, we have to operate the transistors at a little bit higher energy level. Only 2.4 millivolts, so what are we talking about? But if you calculate back to what that means for an AI rack, or what that would mean for a full fab, this 10 angstrom of not controlled in your process leads to tens of megatons of CO2 per year extra. If you take the, actually I did the calculation before the energy prices went up. This is only for a few months ago. Consider what it would be now. We're talking about billions of euros or billions of dollars that you have to spend extra as a AI factory just because those processors are only off by an atom size. So the small variation in the production of those chips has huge impact on the energy outcome and the energy impact as well. It's not just about the money, it's also about the CO2. So, quickly going to how chips then look like, past, present, future. We used to build memory and the compute as close together as possible to have fast connection, less power loss, but at a certain point it just ends. You want more there, there's just no physical space anymore. So we put everything in one die, and that's what happens today. Next step, because it doesn't fit, if you can't fit 1,000 people on a few square 100 meters, what do? You build a skyscraper. And that's actually what is being done. We're stacking. Not just 3D in the transistors themselves, but also chips on top of each other. And that requires a new technology where the industry is moving now. And I'll get to where the opportunity here for Europe is as well. Because in order to do so, you need to have tens of thousands of very small copper connects to actually be able to transfer all the data without too much loss. And those copper connects need to be less than atom flat. You build two chips, you put one on the top of the other, and what happens if those connects are not correct? You either have a non-functioning chip, or even worse, you have a good one and a not so good one, you connect the two, the result is obviously the weakest link, not very good. So you need to be able to control this. Now, if I zoom in a little bit to those stacks, because we're talking about multiple stacks, in the end, and I made an electron microscope picture here, if you don't do this correctly, we're talking here about tens of thousands per chip, less than an atom flat. And it's not completely correct, you get a bonding failure, less efficient chip, and there's that variation already. And that's just one example of what could happen. I won't go into the detail, but there are many things that can go wrong when you produce a chip. So you need to control that. If you can't measure it, you cannot make it. And it's not just the bonding. It's also still shrinking. We all know ASML. Keep on pushing the limits there to make even smaller lines, smaller transistors. It's going to very strange 3D architectures. And like I said, this advanced packaging and stacking. Advanced packaging stacking is where opportunity lies for Europe for sure. The world is dividing now. If Europe is quick, we can still play a role here. Now, so what do we do then? As a deep tech scale-up, now 10 years old, we make machinery that control that process. So you have parties that make machines that make chips, write the lines, and you have parties like us that during process do the measurements. If you can't measure it, you can't make it. All the way through the line, all the way through the stack in the line. We have two products now currently out and deployed over the world at the large chip manufacturers. And we do that actually not by using light or electrons, but we use it by doing atomic force microscopy. Having an atomically sharp needle, bring that very close to what you want to measure. Atoms start feeling each other, van der Waals forces. And when you then scan that needle over the surface, you get a real 3D measurement. And that's what we want. Everything is 3D. The transistor itself, the stacking, want to measure the flatness or the roughness of those copper pads. And a known academic technology, but we brought it to industry level that it can be used in line. A typical deep tech scale-up from a research institute, spun it out, built up the company, and built these systems. Now, I spoke about full dies. The first product that we had is capable of measuring few by few micrometers, which is enough to measure a transistor. But if you want to know if your full die is okay, you want to measure that over 30 by 20 millimeters. And that's the second product that we're now bringing to market. We actually have brought to market, where we can still have that atom scale resolution in 3D, non-destructive, but over a full die, and measure that without stitching, without having to combine multiple images and making sure that I'm quite sure that you miss something. Now, there are a lot of metrology challenges. I won't go in all the detail of all the technology, but if you're producing logic, if you're producing memory or VNAND or DRAM or on-chip lenses, you all have your metrology issues, your process control issues. The one larger than the other, but all are in the nanometer range, and most of them, if not all of them, are becoming 3D challenges. And that's what we're trying to tackle here. And you recognize the hybrid bonding or the advanced packaging at the bottom, but also the 3D chips themselves, which we're able to measure. Now, I spoke a bit about advanced packaging. I can't show you any examples because that is so customer sensitive that I'm not allowed to share any pictures, and seeing a blurred picture is not much fun. But I can show you a little bit about high-NA EUV metrology, the technology that ASML brings to market to make these next node 2 nanometer, 1.8 nanometer chips, where they are extremely three-dimensional, which normal measurement technology cannot measure anymore. And what we are able to do is to actually look at such a chip, look at the die, and be able to measure in 3D, and you actually can see defects here. And we're talking here about a few atoms that are actually placed wrong. And these are those variations that in the end will lead to this billions of dollars of extra energy cost, and even worse, those megatons and megatons of extra CO2 energy to be produced to actually still keep running our data centers that we so urgently need. And here you see what the opportunity for the EU actually is. We focus a lot when we talk about AI on the compute power and the applications that you can do with it. And there's a wild field to play, and we should certainly catch up and play our role with that. But there's a whole industry behind it where actually Europe plays a very important role. Europe is one of the big suppliers to the whole chip manufacturing industry. Not many people realize that, but that is there. So there's this flywheel effect that over the whole world AI explodes, and we should certainly do that also in Europe. But it also means that there's an opportunity for startup scale-ups like us, but also the incumbents, to latch on to that train as well and produce that technology that is needed to produce those chips. And if you talk about sovereignty, in my view, it does not mean that you do everything yourself. Get totally vertically integrated, and we do it as Europe all ourselves. No, what we should do is be the one to actually be able to deliver those technologies that the whole world needs. Then you have leverage. And we have that opportunity. We have that in Europe. Capital remains a problem. Maybe we can talk about it a little bit later. But it's there. Now, if you talk about other extreme examples of three-dimensional measurements, which, by the way, there's a real-life measurement image there, we are now able, and we're unique in this and unique in the world, to do these 3D measurements in line, non-destructively, and supply that to the whole world. It is possible. We have all the major chip manufacturers now have our systems in their factories. That says something. That is not something that happens overnight. It's not something that happens very often. But it does show the potential, the scientific knowledge, the resilience that we do have in Europe. And I fully agree with the ministers that we should not just keep on telling each other that we are running behind, that we are late, that the others are further ahead. So then what should we do? Don't do anything anymore? No. You choose your focus and you move on. And that's what we're trying to do here as a company. Now, briefly a little bit about the company, because we're also here for deep tech, and I see a lot of scale-up founders. It really energizes me to see so many companies when I walk the exhibition hall that have these great ideas, and I see a lot of future there as well for Europe if we just focus it. We were that 10, 15 years ago, founded by Hamed Sadegian, who was supposed to be here on stage, but yeah, sometimes business gets in the way, and he asked me to replace him instead. 10 years ago, as a spin-off from TNO, large Dutch research organization. We're located in Rotterdam, but now also our subsidiaries in, well, actually where all our customers are. Korea, Japan, Taiwan, US. And, well, 2 years ago, we closed our Series C investment round, which then was a very large deep tech round of about 135 million euro investment. And that's what deep tech needs. It's a lot of capital. Typically, deep tech takes 10 years, a few hundred million euros to actually get to your first product and get it in the market. We need that capital. We need to work together there. Now, luckily, we have a strong shareholder base, not just from European shareholders, by the way, because those amounts of money or that appetite even to invest are not there yet. We need to do something about it. On the other hand, it's very good to have those, let's say, cultural diversity in your team and in your board as well to keep you sharp. We've grown out to 450 people, 46 nationalities, of which we are really proud. Diversity really makes it possible. It's too complex, not what we do, to just have it solved by white, gray-haired male like I am. And that is really the only case. And still keep on inventing a lot. We can't stand still, which is patent portfolio protects us partly. You have to keep running and deliver, but we do not stand still in actually developing our technology. And also not stand still in expanding our global base. Europe is not our market, unfortunately. It's too little, no, almost nothing. I'm echoing a bit here what Christophe Fouquet said of ASML. Europe should build up their chip manufacturing as well. Nonetheless, this is a global field. We are a global player, so we're all over the place. Invest a lot. Recently invested in a big new ISO 5 clean room for production. All on our own. And there I would say also still the public-private partnering could be better there. Take more risk from, we take the risk. Governmental funding also takes some more risk, because look what can come out of it. And for the people with keen eyes, they also, no, they don't even see because the chair is in the way. We're also in Belgium, in Leuven. Why? Because we can't do this on our own. We have a large supply chain, but also very good research partners. Like, for instance, IMEC, well known in the semicon industry, is the world-leading institute on next-gen chip development, semiconductor development, where we work together with IMEC, have a system placed there, and their partners, which are our potential customers, to create a technology for the future. We cannot stand still. So, to sum it up, and also to harken back to compute and what was discussed previously, power to compute is power to compete. If you can compute, you can compete. That's why all for this investment in AI in the factories as well. But there's a second-tier effect that we can also deliver the technology that make that worldwide possible. And in order to do so, we should not focus only on the compute factor. There, Taiwan, Korea, US, they are ahead. But the power factor is as important, if not more important. And if you can control that, you are there. So if you turn process control into this nanoscale precision that you need, you create that macroeconomic value. So AI and the process control there is an important lever. And it's a lever that is sometimes not seen. It's a bit of the hidden technology or the hidden driver behind that, and we should certainly not forget that. I hope I gave a little bit of a short overview of what we are working on, but also a little bit of an idea that it is possible to develop these deep tech companies within Europe. It takes resilience, it takes tenacity, it takes a lot of money and a lot of work to obtain that. But if you have that, we have the talent, we have the technology, we have the research institutes, we have the patent base, we have the supply chain. We just need to energize that again. And then it is possible to get to this type of industries and producing the next unicorns in Europe, also in equipment. Thank you. Are there any questions? No, but I'm quite sure you had some
I have
questions.
one. Roland, if you can share the most uncomfortable truth in what you just shared. Is there one most uncomfortable truth?
The most uncomfortable truth. Regarding setting up such a company, perhaps?
Yeah?
That the work is never finished, never stand still. Not when you're 10 years old, not when you're 15 years old, not when you're 20 years old. And when I was young and naive and started this, I thought, well, after 10 years, we get that first product in the field, and then we can start reproducing, manufacturing. Then it will settle down a little bit. Well, less is less. At the airport, I flew in. Sorry, it was on the late stage. Otherwise, I would have taken the train. There are always these management books that you can buy in the bookstore, and they're all about the valley of death that you need to cross.
Right, right.
And you read that, and when you're naive, you say, okay, once we found our product market fit, then we're there. What no one tells you is it doesn't stop there. Then comes the real valley of death.
This is true, yeah.
The scaling, the multiplication, and especially in terms of equipment, you have to build those factories, build them in series, and they should all be the same, which may for software be a little bit less difficult. I will not say it's easy, but less difficult. It's not in those books. I would have really appreciated a book 15 years ago which would have said that.
Makes complete sense, and I completely understand. The journey is never over. For a European founder wanting to build at the very frontier of compute, what's the one thing they need to do differently in 2026 versus 5 years ago? Do you have a good advice for the ones who are?
That's a good one, because the world was really different 5 years ago. In compute, I would say 5 years ago, the world really worked together to advance. Semiconductor was and hopefully still is a very strange industry where everyone of the whole world comes together, write the roadmap for 10 years ahead, down to the last angstrom, and then runs away to compete the hell out of each other. But great, at least it was distributed. You could together get there. Now, with the focus on, let's say, the more national sovereignty, you see that it becomes more difficult. You not only now compete to meet the roadmap, you're also competing amongst countries. And then do not underestimate all the export control regulations. I would say we would even start it too late there. Or let's say 5 years ago, it was not a problem. It was not an issue. You have to have your export license, but that's it. Nowadays, the moment you start developing your product is the moment you start talking to the governments, get deep in, get expertise in, because it's so bloody complicated and changing every day. Don't underestimate that, because it will bite you in the rear the moment you really are there and want to start exporting.
Right.
And that's really different than 5 years ago.
I think that makes a lot of sense. So start quicker with most of these things you normally would push a little further away so
Yeah.
you can keep up with the pace.
Absolutely.
Makes sense.
Don't fall in love only with your technology. It starts with the customer, and unfortunately nowadays in the world it also starts with the other sides, as much as I don't like saying that.
Perfect. Thank you so much, Roland. It was a pleasure having you on board.
Thank you very much.